What if everything you think you know about reality is just the surface of something far stranger, beneath the familiar world we see, at scales so small they defy comprehension? Particles flicker in and out of existence, vanishing one moment, reappearing the next, as if the universe itself is breathing. These are quantum fluctuations, the hidden heartbeat of reality, where empty space isn't really empty at all. It's a seething, unpredictable dance of energy, and it might hold the keys to understanding everything from the birth of the cosmos to the very fabric of time itself. Imagine standing on the shore of an ocean, watching the waves rise and fall. Now picture that same ocean, but instead of water, it's made of particles, some appearing for mere fractions of a second before dissolving back into the void. This isn't science fiction. This is the quantum vacuum, a realm where the rules of physics as we know them twist and warp, where matter and energy play by a different set of rules. And here's the wildest part. These tiny, fleeting changes might be shaping the entire universe in ways we're only beginning to grasp. In this video, we're diving deep into 30 mind-bending theories that attempt to unravel the mysteries of quantum fluctuations. Some suggest these microscopic ripples could be the seeds of entire galaxies, while others argue they might hold clues to parallel universes or even the nature of consciousness itself. We'll explore how something so small could have cosmic consequences, why scientists are both fascinated and baffled by these phenomena, and what it all means for our understanding of existence. Buckle up, because by the end of this journey, you'll never look at the universe the same way again. Think of the fabric of spacetime as a calm, still pond. That's how Einstein's theory of relativity describes it: smooth, continuous, predictable. But zoom in far enough, down to scales a billion times smaller than an atom, and that serene surface starts to look very different. It's not smooth at all. Instead, it resembles a seething, bubbling foam, constantly churning with tiny, fleeting distortions like bubbles forming and popping in a cosmic soda. This is quantum foam, a mind-bending concept first proposed by physicist John Wheeler in the 1950s. In this bizarre quantum landscape, spacetime itself becomes unstable, riddled with microscopic fluctuations where tiny pockets of reality wink in and out of existence. These aren't just mathematical quirks, they could be the fundamental building blocks of the universe. Picture a stormy ocean where waves crash and swirl unpredictably, except instead of water, it's the very fabric of reality itself. One moment, a tiny bubble of spacetime forms, the next it collapses. Some theories even suggest that within these bubbles, the laws of physics might briefly twist into something unrecognizable, creating fleeting alternate realities or warping gravity itself. Why does this matter? Because if spacetime is truly this chaotic at the smallest scales, it could explain some of the biggest mysteries in the cosmos. Take black holes, for example. At their edges, where gravity becomes unimaginably strong, the foam-like nature of spacetime might break down entirely, blurring the line between existence and nothingness. Or consider the early universe. Quantum foam could have played a role in its explosive birth, with random fluctuations seeding the first structures that grew into galaxies. Even gravity, the force that shapes the cosmos, might emerge from this bubbling quantum sea in ways we're only beginning to understand. Wheeler's theory forces us to confront a startling possibility. What we perceive as the smooth, orderly universe might just be an illusion, a kind of cosmic averaging effect, like seeing a forest from far away instead of individual leaves. But down in the quantum foam, reality is wilder, messier, and far more mysterious than we ever imagined. But if quantum foam shows us how spacetime itself bubbles with uncertainty, then virtual particles take that chaos one step further, because sometimes that bubbling energy isn't just distorting empty space. Sometimes it creates matter. In the quantum world, pairs of particles and their antimatter counterparts can spontaneously emerge from nothingness, existing for barely a flicker before annihilating each other and vanishing again. These aren't hallucinations or mathematical tricks, they're real, measurable disturbances in the fabric of reality, and they've been caught in action. One of the most striking proofs comes from something called the Casimir Effect. Picture two uncharged metal plates placed incredibly close together in a vacuum, so close that the gap between them is narrower than the wavelength of most virtual particles popping into existence around them. Outside the plates, these particle pairs form freely, their fleeting lives creating subtle pressure, but between the plates, only the tiniest, highest energy fluctuations can fit. The result, an imbalance. The outside pressure becomes stronger, pushing the plates together as if invisible hands were squeezing them. This isn't theory. It's been measured in labs, proving that empty space isn't passive. It's a roiling sea of temporary creations and destructions. What's wild is that this effect might hold clues to one of cosmology's biggest mysteries, dark energy. If virtual particles constantly emerge and vanish, they should contribute energy to the vacuum of space itself. Calculations suggest this energy should be enormous enough to rip the universe apart. Yet our cosmos expands at a far slower rate. This discrepancy, called the vacuum catastrophe, hints that we're missing something fundamental. Some theories propose that virtual particles interact with gravity in ways we don't yet understand, or that their energies cancel out in hidden dimensions. Others wonder if these fleeting particles could be the pressure behind dark energy itself, gently stretching spacetime from within. And then there's the expansion of the universe. If virtual particles constantly add and subtract energy from the vacuum, could their net effect be driving galaxies apart? It's a tantalizing possibility, one that blurs the line between quantum whimsy and cosmic destiny. After all, if something as ephemeral as a particle flickering into existence for a fraction of a second can nudge metal plates, what else might it be nudging on the scale of the universe? The more we learn about these ghostly particles, the more they seem like cosmic puppeteers tugging at the strings of reality in ways we're only beginning to perceive. Even in absolute darkness, at the coldest temperatures the universe can produce, empty space still hums with an eerie kind of energy, a restless vibration that can never be silenced. This is zero-point energy, the lowest possible energy state of a quantum system where particles never fully settle into stillness. The name might sound peaceful, but there's nothing tranquil about it. Think of it like a guitar string that can never stop vibrating, no matter how gently you pluck it. Even at absolute zero, when all classical motion should freeze, the quantum world refuses to sit still. The implications are staggering. If nothingness is actually a seething ocean of energy, could we one day tap into it? The idea has fueled decades of speculative science and no shortage of wild claims. Some propose zero-point energy as the ultimate power source, a limitless reservoir hiding in the fabric of space itself. Imagine a universe where energy shortages don't exist, where engines run indefinitely by sipping from this cosmic well. It's the kind of idea that feels ripped from science fiction, and for good reason. The challenges are monumental. Here's why physicists remain skeptical. First, zero-point energy is everywhere, but it's also perfectly balanced. Like a stormy sea where every wave is matched by an equal trough, the net effect usually cancels out. Extracting usable energy from it would be like trying to bottle individual raindrops from a hurricane. Worse, the energy density is unimaginably high. Mathematical models suggest the vacuum of space might contain more energy than all the matter in the universe combined. If we could somehow access even a coffee cup's worth, the results could be catastrophic, unleashing enough power to vaporize planets. Yet the dream persists in part because nature itself might already be using it. Some theories suggest zero-point energy could explain the Casimir effect we mentioned earlier, those phantom forces pushing metal plates together. Others wonder if it plays a role in the expansion of the universe itself, acting as the hidden fuel for dark energy. And then there's the tantalizing possibility that zero-point fluctuations could stabilize exotic matter, the kind needed for warp drives or traversable wormholes. The debate isn't just about engineering, it cuts to the heart of how we understand reality. Quantum mechanics tells us the vacuum is alive with potential, but translating that potential into practical energy would require rewriting the rules of physics as we know them. For now, zero-point energy remains a paradox, a force so ubiquitous it's literally woven into the void, yet so elusive we might never hold it in our hands. But that's the allure of quantum mysteries. They tease us with possibilities just beyond our grasp, reminding us that the universe still has secrets left to surrender. What if our universe is just a cosmic hiccup, an accidental blip in an endless sea of nothingness? This is the radical possibility at the heart of quantum cosmology, where the Big Bang isn't the beginning of everything, but rather the offspring of a random quantum fluctuation in a void that existed long before time as we know it. Picture an infinite ocean of absolute stillness, where nothing happens for eons until suddenly, without warning, a single bubble forms. Not a bubble of soap or air, but of spacetime itself, swelling uncontrollably until it becomes everything we see, know, and are. This idea turns the traditional Big Bang narrative on its head. Instead of a singular explosion from an infinitely dense point, the universe emerges from the same quantum unpredictability that lets particles pop in and out of existence in a lab. It's as if the void had a momentary lapse in concentration, a quantum sneeze, and our cosmos was the result. Some versions of this theory suggest these fluctuations aren't rare at all. In an eternal, featureless void, universes might spring up constantly like bubbles in a boiling pot, each with its own unique physics, dimensions, and fate. Ours just happens to be one where life could arise to ponder its origins. The math behind this isn't pure speculation. It ties into the no-boundary proposal developed by Stephen Hawking and James Hartle, which imagines the birth of the universe as a smooth, self-contained event without a sharp edge or singularity, like the North Pole of Earth, where lines of longitude converge but don't actually contain a boundary. In this view, time itself becomes fuzzy at the universe's origin, blending seamlessly into the quantum foam that birthed it. There's no before the Big Bang because time as we understand it didn't exist yet. Instead, the universe simply transitions from possibility to reality, like a word forming on the tip of reality's tongue. Critics argue this pushes quantum mechanics far beyond its tested limits, applying rules governing particles to the entirety of existence. But supporters counter that if quantum laws truly are fundamental, they should apply to the cosmos as a whole. After all, if tiny fluctuations can create particles from nothing, why not entire universes? The staggering scale might be different, but the underlying principle could be the same. A reminder that the universe has a habit of recycling its wildest ideas across every level of reality. And if that's true, it means our existence might not be a singular miracle, but one flicker in an endless cosmic symphony of spontaneous creation. To understand how the universe grew from a near-perfect soup of energy into the intricate web of galaxies we see today, we need to rewind to a fraction of a second after the Big Bang, when space itself expanded faster than light in a mind-bending phenomenon called cosmic inflation. Picture blowing up a balloon with tiny, random wrinkles on its surface. Now, imagine inflating that balloon to the size of the observable universe in less time than it takes light to cross an atom. Those microscopic wrinkles, they'd stretch into vast mountain ranges and valleys across the cosmos. That's essentially what happened during inflation, but instead of wrinkles on rubber, we're talking about quantum fluctuations embedded in the fabric of spacetime itself. These fluctuations weren't just tiny ripples, they were the seeds of everything. As inflation stretched space exponentially, it also magnified those quantum jitters, locking them into the early universe like cosmic fingerprints. When inflation finally ended, those stretched-out fluctuations became slight density differences, regions where matter was ever so slightly more or less packed together. Gravity then got to work pulling denser areas into clusters that would eventually become galaxies, while emptier zones expanded into the vast cosmic voids we see today. It's a staggering thought, the grand architecture of the universe, from the largest superclusters to the emptiest stretches of darkness, might trace back to randomness on a scale trillions of times smaller than an atom. The proof is written in the oldest light we can see, the cosmic microwave background, a faint glow from when the universe was just 380,000 years old. This ancient light isn't perfectly uniform. It's speckled with tiny temperature variations, hotspots and cold spots differing by less than 100,000th of a degree. These imperfections match the predictions of quantum fluctuations stretched by inflation almost perfectly. It's as if we're looking at a baby picture of the universe, and the freckles on its face are the amplified echoes of quantum chaos from the first moments of existence. But here's where it gets even wilder. Without those initial quantum irregularities, the universe might have remained a featureless sea of particles, never clumping into stars or planets. In a strange way, the imperfections we see today, the uneven distribution of galaxies, the voids between them, aren't flaws. They're the signatures of a universe built on quantum uncertainty, where randomness became the blueprint for structure. Some theories even suggest that different regions of space stretched by inflation could have wildly different properties, like bubbles in a multiverse foam, each with its own unique physics. Our observable universe might just be one quiet neighborhood in a far stranger cosmic metropolis, all thanks to quantum fluctuations that refuse to play by the rules. The idea of a single universe feels almost quaint when you consider the sheer explosive potential of quantum fluctuations. If these tiny ripples in spacetime can birth particles from nothing, why stop there? Some theories suggest they might be constantly birthing entire universes, each a self-contained bubble with its own unique physics, floating in a vast multiverse ocean. Picture a pot of water coming to a boil, with bubbles forming, rising, and popping at random. Now imagine that pot is infinitely large, the water is the quantum vacuum, and each bubble is a universe like ours or something far stranger. This isn't just science fiction, it's a serious hypothesis called eternal inflation, where the rapid expansion of spacetime during the universe's first moments never truly stops. Instead, it keeps happening in patches, with quantum fluctuations triggering new, bubble universes to pinch off and inflate on their own. Each bubble could have different fundamental constants, maybe one where gravity is stronger, another where light travels slower, or even universes with extra dimensions curled up in ways we can't begin to visualize. Our universe, with its finely tuned laws allowing for stars, planets, and life, might just be one lucky roll of the dice in an endless cosmic casino. String theory adds another layer to this dizzying vision. The landscape of possible universes predicted by string theory is vast, perhaps 10 to the power of 500 distinct configurations, each representing a different set of physical laws. Quantum fluctuations could be the mechanism that randomly samples this landscape, spawning universes with every possible variation. Think of it like a cosmic slot machine where each pull creates a new universe, and ours happen to land on the rare combination where atoms, chemistry, and life are possible. But how would we ever know? If these bubble universes exist, they're likely forever beyond our reach, separated by stretches of inflating space expanding faster than light. Some might collide with ours, leaving scars in the cosmic microwave background, ancient bruises from long ago encounters with other realities. Others could be so alien that their physics wouldn't even register as real to our instruments. Yet the mere possibility reshapes how we think about existence. If the multiverse is real, then the question isn't, why does our universe have these specific laws? But rather, what doesn't every possible universe exist somewhere, critics argue this veers into metaphysics, a dazzling idea with no way to test it. But supporters counter that the math fits, and nature rarely limits itself to single copies. After all, we once thought Earth was the only planet, then the only star system, then the only galaxy. Each time, the universe proved vaster and more varied than we imagined. If quantum fluctuations can twist spacetime on the smallest scales, why wouldn't they do the same on the grandest? The multiverse might be the ultimate expression of quantum unpredictability, not just flickering particles, but entire realities blooming and fading in an infinite sea of possibility. Time might feel like the most constant, undeniable part of reality, always flowing forward, steady and unshakable. But what if that's just an illusion? At the deepest levels of quantum physics, some theories suggest time itself could be flickering in and out of existence, emerging from the same chaotic sea of fluctuations that birth particles from the void. Imagine a clock that doesn't just tick, it stutters, vanishing between moments like a light bulb with a loose connection. This isn't a malfunction. It might be how time actually works at the Planck scale, where the universe operates in increments so small, even our most precise instruments can't measure them. The idea hinges on a radical rethinking of space-time. In classical physics, time is treated as a smooth, continuous backdrop against which events unfold. But quantum gravity theories like loop quantum gravity or string theory propose that spacetime could be granular, made up of tiny, indivisible chunks. At this scale, time wouldn't flow like a river. Instead, it would behave more like a flipbook, with each frame popping into existence thanks to quantum fluctuations. Between these frames, there might be no time at all, just a frothy, indeterminate state where past and future blur into meaninglessness. This raises bizarre questions about causality, the bedrock principle that cause must always precede effect. If time flickers, could events briefly happen in reverse or even loop back on themselves? Some models suggest that at the Planck scale, the very idea of before and after might break down entirely, leaving only a network of probabilistic connections. Think of it like a movie reel where the frames aren't just out of order. Some scenes might be playing simultaneously, overlapping in ways that defy logic. Experiments with entangled particles already hint at this strangeness, where actions performed on one particle seem to instantaneously affect its partner, as if time and space aren't the rigid separators we assume. And then there's the unsettling possibility that time might not be universal. Just as quantum foam makes spacetime bumpy at tiny scales, time could flow unevenly, running fast in some quantum pockets, slow in others, or even pausing altogether. If true, this would mean now is a local phenomenon, not a cosmic constant. Your present moment and the present moment of a particle halfway across the galaxy could be fundamentally out of sync, with no master clock to reconcile them. The implications ripple outward. If time emerges from quantum processes, then the Big Bang wasn't just the birth of space and matter. It might have been the moment time switched on. Some theories even speculate that time could one day switch off again, freezing the universe in an eternal instant. It's a dizzying thought. The arrow of time, the force that gives our lives direction and meaning, might just be a temporary glitch in the quantum code, a fluctuation that, like all others, could someday collapse back into the void. One of the most provocative ideas in quantum physics suggests that reality itself might depend on something far more mysterious than particles or forces, human consciousness. This is the core of the von Neumann-Wigner interpretation, a theory so radical it blurs the line between observer and observed, proposing that the act of measurement doesn't just record quantum states but actively creates them. Picture a universe where particles exist as ghostly probability waves until a conscious mind looks at them, forcing those waves to collapse into definite outcomes. In this view, quantum fluctuations aren't just random noise, they're the raw material of reality, waiting to be shaped by perception. The implications are staggering. If consciousness truly dictates quantum behavior, then the fundamental building blocks of the universe might be inextricably linked to awareness itself. Think of Schrödinger's famous cat, both dead and alive until observed. But here, it's not just about a cat in a box. It's about whether stars, galaxies, or even spacetime remain in a hazy superposition until some form of consciousness interacts with them. Proponents argue this could explain why quantum systems behave differently when measured like an electron deciding whether to act as a particle or wave only when we pay attention. Critics, however, point to a far less mystical alternative, decoherence. This mainstream explanation argues that quantum systems lose their superposition not because of consciousness, but through inevitable interactions with their environment. Imagine tossing a coin in a vacuum. It might spin undisturbed for a long time, but in the real world, air molecules bump into it, making it settle heads or tails. Similarly, particles constantly jostle against other particles, radiation, or even stray photons, which records their state without needing a conscious observer. Decoherence explains why quantum weirdness seems confined to microscopic scales. Larger objects are constantly measured by their surroundings before our brains ever get involved. Yet the debate persists because of one glaring oddity, the measurement problem. Why does observation, conscious or not, seem to play any special role in quantum mechanics? The von Neumann-Wigner interpretation takes this puzzle to its logical extreme, suggesting that reality remains fluid until a mind solidifies it. Some modern variations even speculate that consciousness might emerge from quantum processes in the brain, creating a feedback loop where mind and matter shape each other. The controversy highlights a deeper tension in physics between the cold, objective universe of equations and the messy, subjective experience of being alive. Most physicists favor decoherence because it relies on measurable interactions, not metaphysical assumptions. But the allure of consciousness collapse theories endures because they offer something science often avoids: a universe where mind and reality aren't just connected but inseparable. Whether that's profound truth or poetic speculation, it forces us to confront the strangest question of all: does the cosmos dream itself into existence, one observation at a time? Dark matter has been called the universe's greatest unsolved mystery, an invisible substance that outweighs all visible matter 5-to-1, yet refuses to interact with light or anything else we can directly detect. But what if its elusiveness isn't just a quirk of nature? What if dark matter's ghostly behavior stems from its origins in the quantum foam itself? Some of the boldest theories in physics suggest that dark matter particles aren't just passing through unseen dimensions or hiding in plain sight. They might be quantum fluctuations given physical form. Imagine the quantum vacuum as a turbulent ocean, where waves aren't just ripples of energy but entire particles flickering into existence. Most vanish instantly, but what if some fluctuations, instead of annihilating, stabilize? Certain models propose that dark matter could be made of particles that freeze out of this quantum chaos, lingering just long enough to clump into vast, invisible halos around galaxies. These wouldn't be ordinary particles bouncing off each other. They'd be shadows of quantum uncertainty, woven into the fabric of space in ways that make them nearly impossible to touch or see. One compelling twist comes from theories involving extra dimensions. In string theory, our familiar three-dimensional space might be floating in a higher dimensional bulk, where quantum fluctuations could give rise to particles that leak into our universe only gravitationally, perfectly explaining why dark matter feels gravity but ignores light. Picture a room filled with floating balloons. If ants lived on the surface of one balloon, they'd have no way to perceive ants on another balloon except through faint tugs on their own. Similarly, dark matter might be vibrations in hidden dimensions, brushing against our universe only through the gentlest gravitational whispers. Even stranger are proposals linking dark matter to actions, hypothetical particles so lightweight they behave less like matter and more like quantum waves. Actions could arise from fluctuations in a previously undiscovered quantum field, condensing into a diffuse, galaxy-spanning mist. Experiments like ADMCs are hunting for these ghostly ripples by tuning ultra-sensitive detectors to the precise frequency actions should ring at, like listening for a cosmic hum buried in the static of empty space. But the wildest idea, dark matter might not be particles at all, but flaws in spacetime itself, knots or defects left over from when the quantum foam first froze into the structured universe we know. Think of it like cracks forming in ice as it solidifies. These primordial imperfections could have stretched to cosmic scales during inflation, carrying mass without being made of any traditional substance. If true, dark matter wouldn't just inhabit space, it would be a relic of space's own turbulent birth. The challenge is testing these theories when dark matter's signature is absence rather than presence. Yet each hypothesis offers a tantalizing clue. If quantum fluctuations can birth particles from nothing, why not the universe's dominant form of matter? The answer might rewrite not just cosmology, but our understanding of how reality stitches itself together at every scale, from the infinitesimal to the infinite. The universe might be the most elaborate illusion ever conceived, not a vast three-dimensional expanse, but a holographic projection painted onto a distant two-dimensional surface. This is the radical promise of the holographic principle, a theory suggesting that everything we see, touch, and experience, every star, every atom, even the fabric of spacetime itself, could be nothing more than quantum fluctuations encoded on the cosmic equivalent of a movie screen. And if that sounds impossible, consider this. The information needed to describe every event inside a room might not be scattered throughout its volume, but etched onto its walls like a cosmic barcode waiting to be read. At the heart of this idea lies the behavior of black holes. When matter falls into a black hole, it vanishes from our universe, seemingly erasing information, a violation of quantum mechanics which insists information can never be truly lost. But in the 1970s, physicist Jacob Bekenstein calculated that a black hole's entropy, a measure of its hidden information, is proportional not to its volume, but to the area of its event horizon. In other words, all the data about what fell in might be compressed onto its two-dimensional surface, like a celestial hard drive. This startling revelation led theorists like Gerard T. Hooft and Leonard Susskind to propose that the same principle could apply to the entire universe. How? Imagine standing in a room lined with tiny pixels, each one fluctuating between ones and zeros. Now, suppose those pixels aren't just displaying an image. They're generating the very reality you're standing in, with every quantum fluctuation on the screen translating into the motion of particles, the curve of spacetime, even the passage of time in your perceived 3D world. The holographic principle suggests our universe works the same way, with quantum fluctuations on a cosmic horizon. Perhaps the edge of the observable universe, acting as the ultimate source code for reality. The implications are dizzying. First, it redefines the nature of quantum fluctuations. Instead of random noise, they become the bits and bytes of existence itself, their interactions weaving the illusion of depth, distance, and dimension. Second, it hints at a profound unity in physics. The long-sought theory of quantum gravity might not require blending general relativity with quantum mechanics. It might emerge naturally from realizing that gravity is a quantum effect, a shadow cast by information processing on a distant surface. But the wildest twist, this could solve the infamous black hole information paradox. If information isn't trapped inside a black hole but smeared across its horizon, then nothing is ever truly lost, just translated into another form, like a book rewritten in a foreign alphabet. Some models even suggest that our universe could be the holographic projection of a lower-dimensional black hole in a higher-dimensional parent universe, making cosmic inflation a kind of data decompression. Critics argue the holographic principle remains untested, its mathematical elegance overshadowed by a lack of experimental proof. Yet supporters point to subtle clues, like the way calculations in quantum field theory mysteriously match those in gravitational theory when framed holographically, as if the universe itself keeps dropping hints that we're reading its blueprint backward. Whether the holographic principle holds the key to reality or not, it forces us to confront a humbling possibility. The cosmos we perceive might just be the surface of something far deeper, stranger, and more interconnected than we ever dared imagine. Dark energy might be the greatest enigma in modern cosmology, an invisible force pushing galaxies apart faster and faster, as if the universe itself is trying to tear itself apart. But what if this mysterious repulsion isn't some exotic substance or undiscovered field? What if it's been hiding in plain sight all along, woven into the quantum fluctuations of empty space? Here's the puzzle. Quantum field theory tells us the vacuum should be boiling with countless virtual particles popping in and out of existence, each contributing a tiny jolt to the fabric of spacetime. When you add up all these fluctuations, the total energy density should be colossal, enough to rip atoms apart before they could even form. Yet when we measure dark energy's actual effect on the cosmos, it's staggeringly weak, about 120 orders of magnitude smaller than predicted. This mismatch, called the cosmological constant problem, is the widest gulf between theory and observation in all of physics. It's like calculating that a candle should outshine the sun, then measuring its glow and finding it barely lights a match. So where does the math go wrong? One possibility is that we're missing a crucial cancellation mechanism, some symmetry or unknown physics that makes most vacuum energy invisible, leaving only a faint residual effect we perceive as dark energy. Think of it like a seesaw with two equally massive children. Their weight should balance perfectly, leaving the board level. But if one child leans just slightly to the side, that tiny imbalance makes the seesaw dip. Similarly, quantum fluctuations might come in pairs that nearly cancel out, with only the slightest leftover, lean, driving cosmic acceleration. Another twist comes from the idea that vacuum energy isn't static, it evolves. Early in the universe, quantum fluctuations might have driven inflation, that brief period of exponential expansion. Then, as the cosmos cooled, the nature of those fluctuations could have shifted, settling into today's gentler but persistent push. It's like swapping a fire hose for a steady breeze, the same underlying mechanism, operating at different intensities across cosmic history. Critics argue these explanations feel like patches on a broken theory, not true solutions. But supporters counter that quantum fluctuations have already reshaped our understanding of reality before. Why couldn't they hold the key to dark energy too? After all, these fleeting disturbances have already birthed particles, twisted spacetime, and perhaps even seeded galaxies. If they're capable of all that, then maybe the accelerating universe isn't a crisis for physics, but a clue, waiting to be decoded from the whispers of the quantum void. We take it for granted that time only flows in one direction. Eggs break but never unbreak, memories form but never unmade. Yet physics can't fully explain why the arrow of time points steadfastly forward when the fundamental laws work just as well in reverse. The answer might lie in the quantum chaos of the early universe, where fluctuations didn't just seed galaxies, they may have locked time itself into an irreversible groove. Picture a deck of cards fresh from the factory, perfectly ordered with suits and numbers neatly stacked. This is the early universe, a state of nearly flawless equilibrium, where entropy, a measure of disorder, was unimaginably low. Now shuffle that deck violently. The cards scatter into randomness, and no amount of reshuffling will restore their original sequence. That's entropy increasing, and it's why we remember the past but not the future. But here's the puzzle. Why was the deck ever ordered to begin with? Quantum fluctuations might hold the key. During cosmic inflation, those microscopic spacetime jitters weren't just stretched into density variations. They also imprinted a subtle bias toward higher entropy states. Think of it like rolling downhill. the universe began at the entropy equivalent of a mountain peak, and quantum fluctuations gave it the tiniest nudge to start descending. Once the slide began, there was no going back. Recent models suggest these fluctuations didn't just create uneven matter distributions, they broke the symmetry of time itself, making one direction statistically favored over the other. It's as if the quantum foam left footprints that only pointed forward. The connection goes deeper. Some quantum gravity theories propose that time's arrow emerges from how quantum systems become entangled with their surroundings, a process called quantum decoherence. Every interaction, every measurement spreads information irreversibly into the environment, like ink dispersing in water. At the universe's birth, quantum fluctuations may have triggered the first irreversible decoherence events, setting the thermodynamic arrow in motion. Imagine a row of dominoes where the first one is tipped by quantum randomness. After that, the cascade has to play out, but the wildest implication: if time's direction depends on quantum fluctuations, other regions of spacetime, or other universes in the multiverse might have arrows pointing backward or sideways from our perspective. We perceive time moving forward because we're caught in the current of our own universe's quantum history. Somewhere beyond our cosmic horizon, time might flow in reverse, with entropy decreasing toward what we'd call the past. It's a staggering thought. The one-way street of time we experience could be a local phenomenon, not a universal law. The mystery isn't just academic. If quantum fluctuations truly locked in time's arrow, they might also hold clues about time's eventual fate. Could entropy someday max out, freezing the universe in eternal stagnation? Or will quantum effects spawn new arrows in unexpected ways? As we peel back the layers of this puzzle, we're left with a profound realization. The flow of time, that most familiar element of existence, might be the universe's greatest magic trick, an illusion woven from the very first quantum whispers of reality. At the heart of every black hole lies a nightmare for physics, a singularity, a point where gravity becomes infinitely strong, space-time curvature becomes infinite, and all known laws of physics break down. But what if singularities don't actually exist? What if they're just artifacts of our incomplete understanding, illusions that vanish when we finally see space-time for what it truly is? A seething, granular fabric stitched together by quantum fluctuations. This is the promise of quantum gravity theories like loop quantum gravity and causal dynamical triangulations, which rewrite Einstein's smooth, continuous spacetime into something far stranger, a patchwork of indivisible building blocks constantly rearranging themselves like pixels on a cosmic screen. Loop quantum gravity takes inspiration from the quantum world's love of discreteness. Just as energy comes in packets and particles have quantized properties, space-time itself might be made of finite loops or atoms of space. Picture a vast spiderweb where each thread carries tiny, quantized amounts of area and volume. These threads twist and reconnect over time, creating the dynamic geometry we perceive as gravity. Near a black hole's core, the loops wouldn't collapse into infinity. Instead, they'd reach a maximum density, like a spring compressed to its limit, then rebound in a cosmic bounce. It's as if the universe has a built-in safety mechanism preventing true singularities, replacing them with quantum fireworks where space-time folds but never truly fractures. Causal dynamical triangulations take a different approach, modeling spacetime as a mosaic of tiny, triangular pieces that constantly flip and rearrange. Imagine assembling a puzzle where the pieces aren't static. They shift positions millions of times per second, creating an average illusion of smoothness at large scales. In this view, black holes aren't bottomless pits but regions where the triangulations become so dense and chaotic that time effectively slows to a crawl, like a computer struggling to render too many polygons at once. Singularities vanish because the underlying structure simply can't cram infinite curvature into a finite number of building blocks. The implications are profound. If these theories are right, then Hawking radiation, the slow evaporation of black holes, might carry subtle imprints of the quantum spacetime structure near the event horizon, like echoes of a hidden geometry. Even the Big Bang could be reinterpreted. Instead of a singularity, it might have been a big bounce, where a previous universe collapsed to the maximum allowed density before rebounding into ours. Yet the challenge remains immense. Unlike quantum fluctuations in particles or fields, spacetime's granularity is absurdly tiny, at the Planck scale, a billionth of a trillionth of a trillionth of a centimeter. Probing this directly is currently impossible, leaving theorists to hunt for indirect clues in cosmic radiation or gravitational waves. But the mere possibility reshapes how we think about reality's extremes. If spacetime is fundamentally quantum, then black holes aren't cosmic dead ends, they're windows into the deepest layer of existence, where fluctuations don't just dance on spacetime's surface but compose its very essence. What if the bizarre behavior of quantum fluctuations isn't just a quirk of nature but a glitch in the system? The simulation argument, popularized by philosopher Nick Bostrom, suggests our universe might be an artificial construct, an ultra-advanced civilization's digital creation. And just as a video game has resolution limits, pixels or frame rates that hint at its engineered origins, quantum fluctuations could be the cosmic equivalent, artifacts of the simulation's underlying code. Imagine running a physics engine so realistic its only tell is the faint numerical noise bubbling up at the smallest scales. That's the provocative idea at the heart of this theory, that randomness isn't random at all, but the procedural backdrop of a programmed reality. Proponents point to unsettling parallels. For one, quantum mechanics operates in discrete packets: energy, spin. Even spacetime itself seemed to come in indivisible units, like the binary bits of a computer simulation. The uncertainty principle, which stops us from knowing a particle's position and momentum simultaneously, mirrors the way a game might save processing power by only rendering details when observed. Even wave function collapse, the eerie way particles choose a state when measured, could be seen as lazy loading, where the universe only calculates definitive outcomes when necessary. And then there's the Planck length, the smallest possible unit of space. Why is there a limit? Perhaps because it's the simulation's pixel size, the finest resolution its hardware can handle. But the theory isn't without critics. Some physicists argue that quantum fluctuations follow mathematical patterns too elegant to be mere computational shortcuts. The equations governing them, like the Schrödinger equation or quantum field theory, are staggeringly precise, predicting behaviors down to 12 decimal places. If we're in a simulation, why would the programmers embed such depth? Others counter that advanced civilizations might use nature's own laws as their codebase, making the simulation indistinguishable from real physics. After all, the best simulations wouldn't feel simulated, they'd feel inevitable. Philosophically, the implications are dizzying. If quantum noise is the static of a virtual universe, does that mean free will is an illusion, just predetermined variables playing out? Or could true randomness in the simulation's algorithms actually allow for genuine unpredictability, even within a constructed world? And what about consciousness? If our minds arise from quantum processes in the brain, as some theories suggest, are we merely subroutines in a grander program? The debate spills into ethics and purpose. Would knowing we're in a simulation change how we live? Some compare it to the Copernican revolution, another humbling reminder that we're not the center of existence. But unlike Copernicus, this theory offers no direct way to test itself. After all, a perfect simulation would, by definition, hide its own seams. Unless, of course, those seams are right in front of us in the quantum static we've been trying to explain for a century. Whether cosmic truth or philosophical thought experiment, the simulation argument forces us to confront a haunting possibility. the universe's most fundamental layer might not be particles or strings, but something far stranger, information itself, flickering in the shadow between reality and code. Einstein's general relativity paints a serene picture of a black hole's event horizon, a smooth, invisible boundary where gravity becomes so strong that not even light can escape. Cross it and you'd float effortlessly inward, unaware of the point of no return, at least in theory. But quantum mechanics flips this tranquil image on its head, suggesting the horizon might be anything but peaceful. Instead, it could be a raging inferno of quantum chaos, a firewall of ultra-high energy particles that would incinerate anything daring to approach. This isn't science fiction. It's the heart of one of modern physics' most heated debates, pitting Einstein's elegant spacetime against the unruly quantum world in a clash that could rewrite our understanding of black holes. The paradox starts with Hawking radiation. As quantum fluctuations near the horizon spawn particle pairs, one falls in while the other escapes, slowly stealing the black hole's mass. But here's the catch: for this process to conserve quantum information, a sacrosanct rule, the escaping radiation must be intricately linked or entangled with its infalling partner. Yet the radiation also becomes entangled with earlier emissions, violating quantum mechanics' rule against doubling entanglement. To resolve this, some theorists propose the infalling particle must be violently severed from its partner, releasing enough energy to transform the horizon into a blistering wall of fire. Imagine stepping onto what you thought was a calm beach, only to find the sand turn to white-hot plasma the moment your foot touches down. This firewall hypothesis doesn't just disrupt Einstein's vision of a smooth horizon, it threatens the very foundation of general relativity. The equivalence principle, which states that free fall feels like floating in empty space, would crumble if horizons were lethal. Worse, it creates a bizarre cosmic censorship. Black holes would be unknowable not because information vanishes inside them, but because anything trying to probe them gets vaporized at the door. Critics argue firewalls are overkill, that subtler quantum effects could preserve information without torching infalling astronauts. Alternatives like fuzzballs in string theory suggest horizons are tangled knots of energy with no sharp boundary, while ER=EPR conjectures that black holes might be bridged to other universes via quantum tunnels, bypassing the need for firewalls entirely. But supporters counter that firewalls are the universe's blunt solution to an impossible paradox. When quantum mechanics and gravity collide, spacetime itself might fracture into flames. The debate forces us to confront a deeper question. What is a black hole's horizon? A mere coordinate in space, a physical barrier, or something stranger, a place where reality, strained to its limits, reveals its quantum scaffolding? Until we solve this, black holes remain cosmic riddles, their secrets guarded either by flames or by laws we've yet to dream of. The moment you try to measure a quantum system, something bizarre happens. The delicate dance of possibilities collapses into a single outcome. But why, and what role do those unpredictable quantum fluctuations play in this fundamental mystery? Depending on which interpretation of quantum mechanics you ask, the answers range from the philosophical to the downright cosmic. Take the Copenhagen interpretation, the old god of quantum theory. Here, fluctuations aren't just background noise, they're the chaotic sparks that force the universe to make a choice. Picture Schrödinger's cat suspended in its infamous superposition of alive and dead. According to Copenhagen, the act of measurement, whether by a conscious observer or a stray photon colliding with the system, triggers a fluctuation that chooses one state over the other. It's as if reality hesitates until the last possible moment, then commits to a path at random. But not everyone buys this observer-centric view. Enter the many worlds interpretation, where fluctuations don't collapse anything, instead, they branch the universe. Every quantum event, no matter how small, becomes a fork in the road, spawning new timelines where all possible outcomes play out. In this dizzying landscape, the cat isn't just alive or dead. It's both in parallel universes splitting like cosmic tree roots. Here, fluctuations aren't arbiters of reality, but the threads weaving an ever-expanding multiverse tapestry. The wrinkle, we only experience one outcome, trapped in a single thread of the grand design. Then there's objective collapse theories, which propose a middle ground. They suggest wave functions collapse spontaneously, not because of observers or branching, but due to inherent instability in the quantum fabric itself. Fluctuations here act like tiny tremors, nudging superpositions toward definitive states once they reach a critical threshold. Think of it like a pencil balanced on its tip. It might teeter momentarily, but eventually some microscopic vibration will knock it over. In this view, the universe has a built-in stopwatch for uncertainty, ensuring quantum weirdness can't scale up indefinitely. The debate isn't just academic, it shapes how we understand reality's bedrock. Copenhagen treats fluctuations as the universe's dice rolls. Many worlds sees them as cosmic DNA replicating endlessly. An objective collapse frames them as quiet regulators keeping quantum chaos in check. Each interpretation offers a radically different lens on why particles behave one way here and another there. And until we crack the measurement problem, these fluctuations remain both the question and the answer, the hidden hands shaping reality's deepest mysteries. Most of us assume reality stays the same whether we're looking at it or not, that objects have definite properties even when unobserved. But quantum mechanics famously disagrees, suggesting particles exist in fuzzy superpositions until measured. So why does the world appear so stable and concrete to our senses? Enter quantum Darwinism, a radical theory proposing that certain quantum fluctuations get selected through a survival of the fittest process, where only the most stable, observable states persist long enough to shape our classical reality. It's as if the universe itself performs a grand experiment, testing which quantum possibilities can withstand the relentless scrutiny of their surroundings. Picture a dense forest where countless seeds sprout randomly, but only those with traits suited to the environment grow into full trees. Similarly, quantum systems constantly generate fluctuations, fleeting states where particles could be here, there, or both simultaneously. But when these fragile superpositions interact with their environment, whether through stray photons, air molecules, or even the gravitational pull of distant stars, most collapse almost instantly. Only a select few configurations prove robust enough to leave lasting imprints, broadcasting their information widely enough for multiple observers to agree on a single version of events. This repeated copying of stable states into the environment is why we all see the same moon in the same phase, not because quantum weirdness vanishes, but because certain outcomes prove better at replicating themselves across reality. This theory flips traditional measurement problems on their head. Instead of asking why observations collapse wave functions, quantum Darwinism suggests the question itself is backwards. Collapse isn't the mystery, it's the persistence of classical reality that needs explaining. In this view, the universe isn't passively waiting to be observed. It's actively filtering its own quantum noise through environmental interactions, amplifying only the fluctuations capable of creating consensus. Think of it like a whisper in a crowded room. Most fade unnoticed, but a few get repeated enough to become common knowledge. Experimental evidence is already emerging. Delicate lab setups called quantum Darwinism spectrometers track how quantum systems imprint information on their surroundings. When photons scatter off an object, for instance, they don't just carry random data. They redundantly encode the object's most stable properties, like its position or momentum. It's these redundant imprints, not some mystical observer effect, that forge our shared reality. The implications stretch beyond physics. If perception relies on environmental consensus, could other conscious beings evolve to perceive entirely different, classical worlds from the same quantum substrate? The answer might depend on which fluctuations their ecosystems learn to amplify. Critics argue this merely repackages the measurement problem rather than solving it. But supporters counter that it shifts the focus from human observation to universal processes, grounding quantum mechanics in tangible interactions rather than philosophical abstractions. After all, nature has no obligation to conform to our intuitive expectations. It only needs mechanisms that work. And if quantum Darwinism is right, those mechanisms might be playing out all around us, in every collision, every chemical bond, every photon bouncing off a surface, quietly shaping the world by deciding which possibilities survive. Quantum field theory doesn't just describe particles, it describes reality as a symphony of invisible waves, each vibrating at its own distinct frequency. Imagine plucking every possible note on a guitar string simultaneously, from the lowest hum to pitches so high they'd shatter glass. Now replace the string with the fabric of spacetime itself, and you've got the mathematical heart of quantum fluctuations, harmonic oscillators humming at every conceivable frequency, filling the universe with an eternal, unseen resonance. But here's the catch. In quantum field theory, each of these oscillators carries a tiny bit of energy, even in its lowest possible state. When you add up all these energies across infinite frequencies, the total should theoretically be infinite. A nonsensical result that would make the vacuum of space infinitely dense with energy, tearing reality apart before it even began. This is the infamous zero-point energy problem, and it's one of the biggest headaches in modern physics. To tame this infinity, physicists use a clever trick called renormalization. Think of it like balancing a budget where expenses keep ballooning out of control. Instead of letting the numbers spiral, you acknowledge that some expenses, like the infinite energy of the vacuum, are artifacts of how we're doing the math, not actual physical quantities. By carefully subtracting these infinities from equations like cosmic bookkeeping, you're left with finite, measurable results that match what we observe in experiments. It's as if the universe has hidden receipts and we're just learning how to itemize them. Renormalization isn't just mathematical sleight of hand. It's a lifeline that lets quantum field theory make stunningly accurate predictions, like the magnetic moment of the electron, calculated to precision, matching experiments within a hair's breadth. But the infinity problem lingers like a shadow, hinting that our theories are still incomplete. Some physicists argue renormalization is a temporary fix, a patch over deeper physics we don't yet understand, perhaps hidden dimensions, undiscovered symmetries, or a radical rethink of spacetime itself. What's wild is that these infinite energies aren't purely theoretical. They show up in tangible ways, like the Casimir Effect we discussed earlier, where metal plates feel a measurable force from the limited fluctuations between them. It's as if the universe is whispering, yes, the math breaks down here, but look closer and you'll find footprints of something real. Whether those footprints lead to a deeper theory or just stranger math, one thing's certain: the quantum vacuum is anything but quiet, and its infinite hum might be the most profound silence we'll ever try to hear. Einstein's spooky action at a distance, quantum entanglement, has always felt like magic. Two particles separated by light years somehow mirror each other's states instantaneously, as if space and time don't apply to them. But what if this phenomenon isn't just a cosmic quirk? What if entanglement is literally bending spacetime itself, stitching the universe together with invisible threads we've only begun to recognize? This is the wild promise of the ER=EPR conjecture, a theory so bold it suggests every entangled pair of particles might be connected by a microscopic wormhole, a tunnel through the fabric of reality, hidden in plain sight. The idea merges two of Einstein's most radical contributions. In 1935, he and Nathan Rosen theorized that black holes could be connected by bridges, later dubbed Einstein-Rosen bridges or wormholes. That same year, with Boris Podolsky and Rosen again, he highlighted entanglement's absurdity, EPR paradox, calling it spooky because it defied classical physics. For decades, these concepts lived separately until physicists Leonard Susskind and Juan Maldacena proposed their two sides of the same coin, their conjecture. Every instance of quantum entanglement epoch is geometrically linked by an ultra-tiny wormhole too small and unstable to traverse but real nonetheless. Picture two entangled electrons dancing in sync across the galaxy. In standard quantum mechanics, their connection is abstract, a mathematical correlation. But under ER equals EPR, their entanglement physically warps spacetime, creating a fleeting, subatomic tunnel between them. It's as if the universe, faced with the paradox of instantaneous connection, cheats by folding spacetime like a sheet of paper, poking a tiny hole where the rules of distance don't apply. These wormholes wouldn't look like sci-fi vortexes, they'd be quantum fluctuations frozen in mid-collapse, spacetime's desperate patch for a deeper inconsistency. The implications rewrite how we think about quantum information. When a particle falls into a black hole, its entanglement with an external partner might not just be a mathematical link, it could form a literal escape route for information, threading through a wormhole to avoid vanishing forever. This could solve the black hole information paradox, ensuring data isn't lost but smuggled out via spacetime's hidden backdoors. Even Hawking radiation, the slow leak of energy from black holes, might carry echoes of these micro-wormholes like whispers passing through a cosmic keyhole. Yet the theory isn't without skeptics. If entanglement creates wormholes, why don't we see their gravitational effects? The answer lies in scale. These structures would exist at the Planck length, a billionth of a trillionth the size of an atom, far too tiny to detect with current tools. Others argue ER equals EPR is more metaphor than mechanism, a poetic bridge between quantum mechanics and gravity rather than a testable fact. But supporters counter that the math holds uncanny symmetries, suggesting nature might not distinguish between information and geometry at the deepest level. The most mind-bending possibility, if ER equals EPR is true, the entire universe could be a vast network of entangled particles, laced together by an invisible web of wormholes. What we perceive as empty space might be a quantum foam not just of particles but of countless spacetime tunnels flickering in and out of existence. It's a vision where entanglement isn't just a feature of reality, it's the glue holding reality together, one quantum stitch at a time. Whether the conjecture survives future tests or not, it forces us to confront a profound truth. The universe might not just contain mysteries, it might be built entirely from them. Time's relentless march forward feels like an unbreakable law, yet at the quantum level, the equations governing reality don't actually distinguish between past and future. So why does the arrow of time point only one way? The answer might be hidden in the chaotic ballet of quantum fluctuations, where microscopic randomness could have etched directionality into the fabric of the cosmos. Picture a deck of cards shuffled into chaos. It's easy to scramble order into disorder, but nearly impossible to reverse the process by chance alone. That's entropy in action, and quantum fluctuations might be the invisible hands that first tipped the scales. At the universe's birth, spacetime was nearly perfectly smooth, a state of extraordinarily low entropy, like a pristine sandcastle before the tide rolls in. Quantum fluctuations during cosmic inflation didn't just create density variations, they also introduced the tiniest statistical biases toward disorder. Think of it like rolling a weighted die over countless repetitions. Even a slight imbalance will eventually skew the outcome. In the early universe, these fluctuations acted as cosmic weights, nudging the young cosmos toward higher entropy states. Once the first domino fell, the rest followed inevitably, locking time into its one-way trajectory. But here's the twist: while individual quantum events are reversible, their collective behavior isn't. A single particle flickering in and out of existence doesn't care about time's direction, but trillions of them, interacting in a dense early universe, create an emergent arrow through sheer statistics. It's like a crowd of people randomly milling about in a room. Each person might move unpredictably, but the group as a whole will inevitably spread out to fill the space. Similarly, quantum fluctuations didn't plan for entropy, they just made it overwhelmingly probable. Recent research suggests this process might even explain why causality feels so fundamental. In quantum experiments, particles can exhibit retrocausality, where future measurements seem to influence past states. But in a universe where quantum fluctuations have statistically favored entropy increase for billions of years, these time-symmetric oddities get drowned out by the macroscopic tide of cause and effect. Imagine trying to hear a whisper in a hurricane. The ambient noise of a time-directed universe overwhelms any fleeting hints of temporal symmetry. The implications stretch beyond cosmology. If quantum fluctuations set time's arrow, other regions of space-time or other universes in a multiverse might have arrows pointing in opposite directions. We perceive time flowing forward because we're embedded in a local pocket where fluctuations conspired to create our familiar past-to-future narrative. Elsewhere, reality might be rewinding or even branching into multiple temporal directions like a cosmic subway map. Critics argue this shifts the mystery rather than solving it. Why did the early universe start in such a low entropy state to begin with? But supporters counter that quantum fluctuations offer a mechanism, not just a description. Like a sculptor revealing a statue hidden in marble, they didn't create time's arrow. They merely uncovered what was always latent in the quantum chaos. Whether this explanation holds or not, one thing's certain. The flow of time, so central to our existence, might be the universe's most elegant accident, a story written in the random pulses of the quantum void. There's a cosmic doomsday scenario hiding in the quantum void, one so utterly final it makes black holes and asteroid impacts seem like minor inconveniences. It's called vacuum decay, a chain reaction where the universe's very foundation tears itself apart, rewriting the laws of physics as it spreads. Imagine lighting a single match in a dry forest, except the forest is reality itself, and the fire burns at the speed of light. This isn't science fiction. It's a legitimate, if unsettling, possibility arising from the same quantum fluctuations that birthed galaxies. Here's how it could happen. Our universe might not be in the lowest possible energy state. Think of it like a ball resting in a shallow valley instead of at the bottom of the deepest canyon. Quantum fluctuations could, purely by chance, nudge a tiny patch of space into a lower energy, true vacuum, creating a bubble where the fundamental constants, like the strength of gravity or the mass of electrons, suddenly change. This bubble would expand in all directions at light speed, its walls rewriting physics as they pass. One moment, stars shine and life exists. The next, atoms might not even hold together, dissolving into a new reality with alien rules. The most chilling part, we wouldn't see it coming. The edge of such a bubble would arrive without warning, giving us zero time to react. One instant, Earth is here, the next, it's something else entirely. The math behind this stems from Higgs field dynamics, the same quantum field that gives particles mass. If the Higgs occupies a metastable state, a temporary resting place rather than true stability, then vacuum decay becomes a matter of when, not if. Some calculations suggest our universe's current configuration could persist for billions of years or collapse tomorrow. There's no way to predict the trigger because it relies on a random quantum fluctuation powerful enough to kickstart the transition. It's like waiting for a radioactive atom to decay, except the atom is spacetime itself. And here's the existential kicker. If vacuum decay is possible, it might have already happened elsewhere. In an infinite universe, a true vacuum bubble could be expanding right now, somewhere beyond our observable horizon. We'd never know until it reached us because the warning signal, light from the catastrophe, would arrive at the same instant as the bubble itself. Some theorists even speculate that vacuum decay could explain why we haven't found advanced alien civilizations. If the universe is old enough, civilizations that master high-energy physics might accidentally trigger their own demise, creating runaway vacuum collapses that sterilize entire regions of the cosmos. But before you panic, consider this: vacuum decay remains highly speculative. The Higgs metastability depends on precise measurements that still have wiggle room, and some models suggest quantum effects could stabilize the vacuum indefinitely. There's also the bizarre possibility that a true vacuum wouldn't destroy life, just transform it into something unrecognizable, a universe where different physics somehow still allow complexity. Still, the mere possibility forces us to confront a humbling truth: the quantum fields underpinning reality might not be permanent. They could be temporary arrangements, cosmic house of cards waiting for the slightest nudge to collapse into a new order. Whether that's terrifying or thrilling depends on how you view the universe: a fragile equilibrium or a canvas eternally repainting itself. Stephen Hawking's greatest scientific legacy wasn't just revealing how black holes evaporate, it was exposing a terrifying paradox at the heart of physics. If black holes slowly radiate away their mass through quantum fluctuations at the event horizon, what happens to all the information about the matter that fell in? According to quantum mechanics, information can never be truly destroyed. But if a black hole vanishes entirely, leaving only thermal radiation behind, that information seems to vanish into oblivion. This contradiction, known as the black hole information paradox, has haunted physicists for decades, and the solution might lie in the chaotic dance of quantum fluctuations at the very edge of reality. Picture a book tossed into a bonfire. In classical physics, the information in that book, its words, its ink, its structure, would seem lost as the pages burn to ash. But quantum mechanics insists that if you could somehow collect every photon, every wisp of smoke, and trace their interactions with infinite precision, you could theoretically reconstruct the book from the ashes. Now imagine that bonfire is a black hole, and the ash is Hawking radiation, a featureless glow of particles born from quantum fluctuations near the horizon. If the radiation carries no trace of what fell in, the information is gone forever, violating quantum law. But if the information somehow escapes, where is it hiding? This is where quantum fluctuations become more than just background noise. They might be the universe's cryptographic system. Recent theories suggest that as particles and energy fall toward a black hole, their information gets scrambled and imprinted onto the chaotic quantum jitters at the event horizon. It's like throwing a message into a whirlpool. The words seem destroyed, but they're actually being churned into the water's ripples in a way that could, in principle, be decoded. These fluctuations don't just emit random particles, they might encode data in subtle correlations between each bit of Hawking radiation, like a cosmic Morse code stitched into the fabric of spacetime. The math behind this is dizzying. Some models propose that the event horizon acts like a quantum computer, performing trillions of operations per second to holographically preserve information on its surface. Others suggest that entangled particles, one falling in, one radiating away, form delicate bridges that ferry information back out, like echoes bouncing between canyon walls. Even the geometry of spacetime near the horizon might warp in ways that records infalling data, with quantum fluctuations serving as the universe's quill, etching history onto the edge of oblivion. But the most radical idea: information might not need to escape at all. If the black hole's interior and exterior remain entangled through quantum fluctuations, then the information never truly enters the hole. It's smeared across the horizon like a shadow cast on a veil. In this view, the paradox arises from our flawed intuition about location, not physics. Just as a hologram stores a 3D image on a 2D surface, a black hole's information could be entirely encoded in its boundary fluctuations, never crossing the point of no return. Critics argue this stretches quantum mechanics to its breaking point, demanding new physics to explain how information survives such extreme conditions. Yet the stakes couldn't be higher. If quantum fluctuations can resolve the paradox, they'd prove that even black holes, the universe's most destructive forces, play by the rules. If not, we might need to rewrite those rules entirely. The answer could redefine reality itself, showing us whether information is truly immortal or if some parts of the universe are forever beyond understanding. What if the universe isn't just governed by quantum fluctuations, but actively uses them to protect its own integrity? This is the mind-bending premise behind the quantum error correction hypothesis, a theory that suggests spacetime itself might function like a cosmic hard drive, with random fluctuations serving as built-in repair mechanisms for reality. Picture a DVD scratched by time, yet somehow the movie still plays perfectly. That's the eerie stability of our universe, and quantum error correction could explain how it maintains coherence across billions of years and light years. At its core, this idea borrows from quantum computing, where fragile qubits are shielded from decoherence, the tendency of quantum states to collapse into noise by spreading their information across entangled networks. If one qubit fails, the data survives redundantly in others, allowing errors to be detected and fixed. Apply this logic to spacetime, and those seething quantum fluctuations might not be glitches. They could be features constantly fine-tuning the fabric of reality to prevent catastrophic information loss. Imagine spacetime as a vast, self-healing mosaic. Every tile looks disordered up close, but step back and the chaos resolves into a stable picture. The math behind this reveals something profound. Certain quantum field theories map perfectly onto error-correcting codes, where local fluctuations behave like the noise the system automatically filters out. In this view, the vacuum isn't just empty, it's a dynamic storage medium, with every quantum field acting like a holographic hard drive. When particles interact or entangled states form, they're not just exchanging energy, they're performing cosmic IT maintenance, ensuring no bit of information slips through the cracks. Even black holes, those infamous information shredders, might not be destroyers after all. Their event horizons could function like error-correcting boundaries, scrambling data not to erase it, but to redundantly encode it in Hawking radiation, like a file compressed across a trillion scattered pixels. But how does this solve decoherence? Think of a symphony where musicians occasionally miss notes. In a traditional setup, the errors accumulate until the melody collapses into noise. But in a quantum error-corrected universe, every instrument is mic'd to 1,000 speakers playing the same score. Lose one violin, and 99 others fill the gap seamlessly. Applied to particles, this means superposition states, those schizophrenic, here and there, moments don't unravel because the system constantly checks their coherence against entangled partners. The fluctuations we observe might be the universe's way of running background diagnostics, tweaking quantum states just enough to keep reality running smoothly. Critics argue this stretches analogies too far, that error correction in labs relies on carefully designed circuits, not random vacuum fluctuations. Yet supporters counter that nature often stumbles upon engineering solutions long before humans do. After all, DNA has been error-correcting itself for billions of years. If biology cracked the code, why not spacetime itself, the theory's boldest claim? That the universe's apparent fine-tuning the precise constants allowing for stars, planets, and life isn't luck. It's the inevitable outcome of a system optimized to preserve information against the ravages of time. Whether this hypothesis holds or not, it reframes quantum fluctuations from cosmic static to potential guardians of order. The void isn't chaotic, it's meticulous, performing quadrillion calculations per second to ensure reality never crashes. And if that's true, then every particle, every force, every ripple in spacetime might be part of the universe's ultimate backup system, a failsafe written in the language of quantum noise. At first glance, the idea that a universe with gravity could be perfectly described by a theory without gravity seems like pure fantasy. like trying to recreate a three-dimensional sculpture using only a flat sheet of paper. Yet this is the astonishing promise of the AD/CFT correspondence, a radical idea in string theory where the quantum fluctuations on a lower dimensional boundary encode the full gravitational physics of a higher dimensional space. It's as if the universe is a hologram, not in the sci-fi sense, but in a mathematically precise way where the information needed to describe every event inside a volume isn't scattered throughout its depth, but meticulously painted onto its edges. To grasp how this works, imagine a can of soup. The soup inside, rich, complex, full of ingredients interacting in three dimensions, represents a universe with gravity, like the anti-de Sitter space AD/S in the theory's name. Now picture the label wrapped around the can. It's flat, two-dimensional, yet contains all the information needed to describe the soup: ingredients, nutrition, even the brand story. In AD/CFT, that label is a conformal field theory, CFT, a quantum system without gravity, where particles and fields interact in one fewer dimension. The mind-bending claim: the label doesn't just describe the soup, it is the soup, with every quantum fluctuation on the flat surface corresponding precisely to a gravitational event in the depths. This isn't just abstract math. The correspondence has been used to solve real problems in quantum physics, like understanding the behavior of quark-gluon plasma, a state of matter so extreme it hasn't existed since microseconds after the Big Bang. By translating these nearly intractable gravitational problems into a more manageable quantum framework, physicists have uncovered insights that would otherwise be hidden. It's like decoding a secret language where the scribbles on the edge of a map reveal the terrain of an entire unexplored continent. But here's where quantum fluctuations take center stage. In the boundary CFT, these tiny, random jitters aren't just noise, they're the building blocks of spacetime itself. A fluctuation in the quantum field might correspond to a gravitational wave rippling through the higher dimensional bulk, or even the creation of a tiny black hole. The more chaotic and entangled the fluctuations on the boundary, the more complex the gravitational phenomena in the interior. This duality suggests something profound. What we perceive as the smooth fabric of space and time could emerge from the collective behavior of countless quantum interactions on a distant, lower dimensional surface. Critics argue the theory has limits. Anti-de Sitter space, with its negative curvature, doesn't perfectly describe our universe, which appears flat or slightly positively curved. Yet supporters counter that AD/CFT is a starting point, a Rosetta Stone for decoding quantum gravity's deeper principles. If true, it means the quantum fluctuations we've been studying for decades aren't just side effects. They're the secret language of reality, whispering the universe's gravitational secrets to anyone who knows how to listen. And that might be the most tantalizing clue yet in our quest to unify physics. Quantum mechanics gives us a universe where particles can be in two places at once, spinning in opposite directions simultaneously, existing in ghostly superpositions until someone looks. Yet the world we experience feels solid, predictable, classical. So how does reality transition from the surreal quantum realm to the clockwork certainty of everyday life? The answer might lie in a process called environmental decoherence, where quantum fluctuations act as the universe's ultimate mediator, constantly nudging fragile quantum states toward classical behavior through countless tiny interactions. Picture a single electron suspended in a vacuum, isolated from all outside influences. Left untouched, it can maintain its delicate superposition indefinitely, spinning both clockwise and counterclockwise in a paradoxical dance. But now introduce a single photon, just one stray particle of light colliding with it. That tiny interaction forces the electron to choose a definite spin state, imprinting information about its new configuration onto the photon. Now scale this up to trillions of interactions, air molecules bumping atoms, cosmic rays zipping through, even the faint tug of distant stars' gravity. Each encounter acts like a miniature measurement, chipping away at quantum weirdness until only classical certainty remains. It's as if the universe is constantly whispering to quantum systems, pick a side. This isn't just theory, it's measurable in the lab. In groundbreaking experiments, physicists have watched as carefully prepared quantum states gradually lose their coherence when exposed to even minuscule environmental noise. A molecule suspended in a near-perfect vacuum might maintain superposition for milliseconds, but add a few stray gas molecules and that time plummets. The more complex the system, the more degrees of freedom it has to interact with its surroundings, the faster it collapses into classical behavior. This explains why we don't see cats or cars in superpositions. Their sheer size means they're constantly bombarded by environmental interactions, drowning out quantum effects before they can manifest. Yet decoherence doesn't actually destroy quantum weirdness, it just hides it from view. The information about a particle's original superposition isn't lost. It's scattered into the environment, smeared across countless interacting particles like ink dissolving in the ocean. In principle, if you could track every photon, every atom that interacted with the system, you could reverse the process and reconstruct the original quantum state. But in practice, that information becomes so hopelessly entangled with the environment that it's effectively irrecoverable, like trying to unmix cream from coffee after stirring. The role of quantum fluctuations here is subtle but profound. They're not just background noise, they're active participants in shaping reality's behavior. The vacuum isn't truly empty, it's a seething froth of virtual particles popping in and out of existence, each one a potential interaction that could nudge a quantum system toward classicality. Even at absolute zero, where all thermal motion stops, zero-point fluctuations ensure this process never fully shuts off. It's as if the universe has a built-in failsafe against perpetual quantum weirdness, a mechanism ensuring that at macroscopic scales, the world behaves the way our intuition expects. This has startling implications for measurement in quantum mechanics. The traditional observer effect isn't about conscious observers at all. It's about any interaction that leaks quantum information into the environment. A photon bouncing off an atom isn't just carrying away light, it's carrying away data about that atom's state, forcing it to commit to a definite position or momentum. In this view, classical reality emerges not from human observation, but from the relentless observation performed by the environment itself, with quantum fluctuations as its trillions of tiny witnesses. Critics argue this doesn't fully solve the measurement problem, it just shifts the mystery from why do observations collapse wave functions to why do we perceive only one outcome when the environment encodes many. But supporters counter that decoherence provides a crucial bridge between quantum theory and lived experience. After all, we don't need consciousness to explain why trees fall in forests with no one around. The air molecules interacting with the tree serve as nature's own recording device. Similarly, quantum fluctuations ensure that reality decoheres, whether humans are watching or not, grounding the abstract mathematics of quantum mechanics in tangible physical processes. The deeper lesson, quantum weirdness isn't gone, it's just hiding in plain sight, woven into the fabric of seemingly ordinary interactions. Every time you touch a table, the reason it feels solid isn't just because of atomic forces, it's because trillions of quantum fluctuations have already done the work of collapsing uncertainties, leaving behind a world that behaves classically. What we perceive as the steady ground beneath our feet is at its core the end product of an unimaginably complex dance between particles and the restless quantum void from which they emerged. The universe's grandest structures, galaxies, clusters, the vast cosmic web owe their existence to the tiniest of tremors, quantum fluctuations magnified to cosmic scales during the universe's violent infancy. In the first sliver of a second after the Big Bang, space itself expanded faster than light, stretching these microscopic ripples into the gravitational scaffolding for everything we see today. Picture a tranquil pond at night, its surface barely disturbed by random raindrops. Now imagine that pond suddenly ballooning to the size of an ocean, transforming each tiny ripple into towering waves frozen in time. That's cosmic inflation's alchemy, turning quantum whispers into the architecture of reality. The math behind this is breathtakingly precise. Quantum field theory predicts that inflation would have stretched fluctuations in the fabric of spacetime, imprinting them with a distinctive fingerprint, a nearly scale invariant spectrum where small and large density variations follow the same statistical pattern. This isn't just theoretical elegance, it's a smoking gun. When astrophysicists map the cosmic microwave background, the afterglow of the Big Bang, they find temperature variations matching these predictions to within 1%. Those subtle hot and cold spots, differing by mere millionths of a degree, are the amplified echoes of quantum jitters from the universe's first trillionth of a second. What's astonishing isn't just the theory's accuracy, but how these fluctuations dictated the universe's fate. Slightly denser regions where quantum randomness piled up extra particles became gravitational wells, pulling in surrounding matter over billions of years. Emptier zones expanded into cosmic voids. It's a cosmic irony. The universe's largest structures trace back to randomness so tiny that if you scaled a single fluctuation to the size of a proton, the region it influenced would now span millions of light-years. The clinching evidence came from missions like Planck and WMAP, which mapped the CMB with unprecedented precision. The data revealed not just the expected fluctuation pattern, but subtle correlations like how hotter spots are slightly more stretched than colder ones, that align perfectly with inflation's quantum origin. It's as if we've found the universe's birth certificate, signed by quantum mechanics in the first, incomprehensibly brief moment of existence, yet mysteries remain. Why did inflation start and stop? Are there even earlier layers of quantum history buried beneath what we can observe? The answers might lie in future measurements of primordial gravitational waves, the ripples in spacetime itself that could carry clues about inflation's energy scale. For now, one truth stands clear. The cosmos didn't emerge from perfect symmetry, but from quantum chaos, a sublime disorder that became the blueprint for all we know. Time might be the most stubborn puzzle in physics, the one thing that refuses to fit neatly into our theories. In general relativity, time is a dynamic player, bending and warping alongside space in the cosmic dance of gravity. But in quantum mechanics, time is just a static backdrop, an unchanging stage where particles perform their probabilistic routines. This mismatch isn't just a technical inconvenience, it's a fundamental crisis that quantum fluctuations have thrown into sharp relief. At the heart of the problem lies a simple but profound question. Is time a fundamental feature of the universe, or is it something that emerges from deeper, timeless processes? Quantum gravity theory's attempts to unify general relativity with quantum mechanics offer wildly different answers. Loop quantum gravity, for example, suggests time might vanish entirely at the smallest scales, with reality consisting of timeless, discrete loops that only give the illusion of temporal flow when viewed from afar. Picture a flipbook where the individual pages are static, but flipping through them creates the illusion of motion. Similarly, the smooth passage of time we experience could be a collective effect emerging from quantum fluctuations in the underlying fabric of spacetime. String theory takes a different approach, proposing that time might be tied to the vibrational states of strings' tiny, one-dimensional filaments whose oscillations give rise to particles and forces. Here, quantum fluctuations don't just disturb spacetime. They might actually define how time behaves, with certain vibrational modes corresponding to the forward arrow we perceive. Imagine plucking a guitar string. The note you hear depends on how the string vibrates. In string theory, time itself could be a kind of cosmic chord, its rhythm set by the quantum hum of countless strings. But the most radical idea comes from the holographic principle, which suggests time might not exist in the bulk of the universe at all, only on its boundary. In this view, quantum fluctuations on a distant, lower-dimensional surface could encode not just space, but time as well, like a movie screen projecting both the actors and the storyline. It's as if the universe is a grand illusion, with time being a narrative constructed from quantum data rather than an intrinsic feature. This would mean our experience of past, present, and future is akin to watching a film. We perceive sequence, but the real itself is timeless. The wild card in all this, quantum fluctuations themselves. If time is emergent, then fluctuations might be the mechanism by which it arises, random jitters that, when averaged over vast scales, create the appearance of continuous flow. Think of a choppy sea viewed from high above. The individual waves are chaotic, but from a distance, the ocean seems to move with smooth, predictable rhythms. Similarly, the universe's clock could be ticking not because time is fundamental, but because quantum noise conspires to make it look that way. Critics argue these ideas push speculation beyond the limits of testability. After all, how do you design an experiment to prove time isn't real? But supporters counter that subtle signatures might lurk in cosmic radiation or gravitational waves, hints that time behaves differently at the extremes of black holes or the dawn of the universe. Whether these theories hold or not, one thing's certain: quantum fluctuations have torn open a fissure in our understanding of time, revealing a mystery that could redefine not just physics, but the very nature of existence. The deeper we dig, the more it seems time, like everything else, might be written in the quantum static, waiting to be decoded. Quantum fluctuations don't just challenge our understanding of physics, they force us to confront the very nature of reality itself. Are these microscopic jitters evidence that the universe is fundamentally mental, a construct shaped by observation? Or do they simply reflect an objective, if chaotic, physical world operating beyond our perception? This divide between idealism and realism is one of philosophy's oldest battlegrounds, and quantum mechanics has reignited it with startling urgency. Take idealism first, the view that reality is fundamentally mental or experiential. Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, suggest that consciousness itself causes wave function collapse. In this radical framework, quantum fluctuations aren't just random noise, they're the unresolved potential of a universe waiting to be observed. Picture a dream where objects only solidify when you focus on them. Until then, they flicker at the edges of perception, half-formed and unstable. If idealism holds, the quantum foam might be the raw material of a participatory universe where reality crystallizes through the act of measurement, or even through conscious awareness itself. Proponents point to the observer effect in quantum experiments, where particles seem to choose definite states only when measured. Could this mean the universe is less a machine and more a collective thought, with fluctuations as the synaptic sparks of a cosmic mind? But realism pushes back hard. This camp argues that quantum fluctuations exist independently of observation, that they're features of an objective, if bizarre, physical reality. Decoherence theory, for instance, shows how quantum superpositions collapse through environmental interactions, no consciousness required. Imagine a tree falling in a forest with no one around. Realists argue the sound still happens because air molecules vibrate regardless of witnesses. Similarly, quantum fluctuations might just be the universe's way of balancing energy at the smallest scales, a dance of virtual particles that would occur even if all observers vanished. Realist interpretations often lean on mathematical rigor, like renormalization in quantum field theory, which tames infinities without invoking observers. For them, the weirdness isn't proof of mental primacy, it's a call to expand our definition of physical, to include entanglement, superposition, and other non-intuitive phenomena. The tension between these views reveals deeper questions. If quantum fluctuations underpin reality, does that mean reality is inherently probabilistic, a tapestry of maybes rather than certainties? Or is the randomness an illusion, masking hidden variables or deeper layers of determinism we haven't uncovered? Pilot wave theory, a realist alternative to mainstream quantum mechanics, proposes that particles have definite positions at all times, guided by unseen pilot waves that create the appearance of randomness. Here, fluctuations aren't primordial chaos but surface ripples on a hidden ocean of order. It's a comforting idea until you realize it requires faster-than-light influences and an invisible scaffolding of waves, trading one strangeness for another. Meanwhile, idealism's critics highlight its slippery slope. If consciousness shapes reality, whose consciousness? A human's, a cat's, a photon's? And how could early universe fluctuations occurring before any observers existed have seeded galaxies? Some idealists sidestep this by positing a universal mind or panpsychism, where consciousness is a fundamental property of all matter. But this veers into metaphysics, leaving many physicists uneasy. Perhaps the truth lies somewhere in the murky middle. Cubism, a pragmatic interpretation, treats quantum probabilities as personal beliefs rather than objective truths. In this view, fluctuations reflect our limited knowledge, not the universe's intrinsic nature. It's like a gambler assigning odds. The uncertainty isn't in the cards but in the gambler's head. Cubism bridges idealism and realism by acknowledging that while reality exists independently, our access to it is always mediated by interaction and interpretation. The debate isn't academic wordplay. It shapes how we approach quantum gravity, cosmology, even artificial intelligence. If idealism is right, probing reality's deepest layers might require understanding consciousness itself. If realism holds, we just need better detectors. Either way, quantum fluctuations have torn open a fissure in our worldview, forcing us to ask, is the universe something we discover, or something we, in some profound sense, create? The answer, much like a quantum superposition, remains tantalizingly unresolved. Scientists have long theorized about quantum fluctuations, but proving their existence requires experiments so precise they border on the miraculous. Today's laboratories are pushing the boundaries of detection, using everything from microscopic metal plates to supercooled atoms in attempts to catch these elusive quantum whispers in action. The Casimir Effect remains one of the most striking demonstrations where two uncharged metal plates placed nanometers apart in a vacuum inexplicably attract each other due to the pressure difference created by restricted quantum fluctuations. Modern iterations of this experiment now use advanced nanotechnology to measure forces smaller than the weight of a single bacterium, with results confirming quantum electrodynamics predictions to astonishing precision. But physicists aren't stopping there. Teams at institutions like MIT and ETH Zurich are attempting to amplify these effects using specialized metamaterials, engineered surfaces with patterns smaller than the wavelength of light. By sculpting materials at nanoscale resolutions, researchers can manipulate how quantum fluctuations interact with surfaces, potentially revealing new aspects of vacuum energy. Some setups even use gold-coated silicon surfaces with precisely calculated grooves, turning the entire apparatus into a quantum fluctuation antenna designed to resonate with specific vacuum modes. Meanwhile, in the quest to observe quantum gravity effects, scientists are getting creative with analog systems. Superfluid helium-3 cooled to near absolute zero can mimic spacetime's behavior, with vortices in the liquid standing in for black holes and quantum fluctuations manifesting as ripples in the fluid structure. When researchers at Lancaster University observed unexpected interactions between these vortices, they might have been glimpsing the quantum foam-like structure predicted to exist at Planck scales. Similarly, Bose-Einstein condensates clouds of atoms chilled until they behave as a single quantum entity, have become testbeds for simulations of expanding universes, complete with analog quantum fluctuations that seed structure formation just like the early cosmos. Perhaps the most ambitious frontier involves gravitational wave detectors. Advanced LIGO unprecedented sensitivity could potentially detect signatures of quantum spacetime fluctuations if they interact with passing gravitational waves. The challenge, distinguishing these minuscule signals from the detector's own quantum noise, a problem requiring quantum squeezing techniques that essentially quiet certain quantum uncertainties to amplify others. It's like trying to hear a pin drop in a hurricane by selectively muffling the wind. Underground laboratories are joining the hunt through ultra-sensitive dark matter detectors. While designed to catch hypothetical particles, these cryogenic setups could also register rare collisions with exotic quantum vacuum fluctuations. The germanium detector array JERDA experiment, buried beneath the Italian Alps, has already set limits on certain vacuum decay scenarios by listening for spontaneous energy releases in pure germanium crystals, a potential smoking gun for vacuum instability. Quantum optics provides another window into this hidden realm. By firing tightly controlled laser pulses into nonlinear crystals, researchers can stimulate the vacuum to produce detectable photon pairs, a phenomenon called parametric down conversion that essentially teases virtual particles into observable existence. Recent experiments at the University of Ottawa have taken this further by engineering quantum light states that interact with the vacuum in unprecedented ways, creating interference patterns that reveal the vacuum's active structure. These experimental frontiers share a common thread. They treat the vacuum not as empty space, but as a dynamic medium with measurable properties. From nanomechanical sensors that vibrate in response to quantum jitters to proposals for detecting unravel radiation, the ghostly glow a violently accelerating particle should see in the quantum vacuum, each approach offers a new lens on reality's turbulent foundations. The ultimate goal, to transform quantum fluctuations from mathematical abstractions into directly measurable phenomena, bridging the gap between theory and tangible observation in our ongoing quest to decipher the universe's quantum code. The future of quantum fluctuation research isn't just about refining equations, it's about building entirely new windows into reality itself. Imagine laboratories where artificial black holes evaporate on tabletops, where quantum computers simulate baby universes, and where telescope arrays scan the sky for fingerprints of spacetime's granular structure. This is no distant fantasy. Teams worldwide are already constructing devices that could revolutionize our understanding of quantum foam, vacuum energy, and the birth of the cosmos. Quantum simulators stand at the forefront of this revolution. Unlike traditional computers that calculate using bits, these specialized machines exploit quantum entanglement to physically mimic other quantum systems, including spacetime itself. At the University of Maryland, researchers are using trapped ion setups to model how quantum fluctuations might behave near a black hole's event horizon. By precisely controlling each ion's quantum state, they create miniature analogs of curved spacetime where virtual particles pop in and out of existence on demand. Meanwhile, in Amsterdam, a team has built a graphene-based simulator where electrons move as if experiencing extreme gravitational forces, essentially crafting a 2D universe with tunable physics. These aren't just experiments, they're wormholes to theoretical realms, allowing us to stress test ideas about quantum gravity that were once purely mathematical. The cosmic hunt for primordial fluctuations is also entering a golden age. Next-generation telescopes like the Simons Observatory and CMB-S4 will map the cosmic microwave background with 10 times the sensitivity of current instruments, searching for subtle polarization patterns called B modes that could reveal gravitational waves from the universe's first quantum tremors. Even more ambitious is the proposed LightBird satellite, designed to peer past the cosmic microwave background's surface glow and detect the reionization bumps, imprints left when quantum fluctuations first stretched during inflation. It's like upgrading from a blurry black and white photo of the early universe to an Ultra HD 3D scan where every pixel carries clues about spacetime's quantum origins. Quantum computing offers another paradigm shift. Companies like Google and IBM are developing algorithms to simulate vacuum fluctuations at scales impossible for classical supercomputers. A 72-qubit quantum processor could model how virtual particles interact in strong gravitational fields, a calculation that would take conventional machines longer than the age of the universe. Researchers at Fermilab have already used quantum annealers to explore how false vacuum decay might propagate, offering glimpses into how our universe could one day rewrite its own laws. The real breakthrough will come when error-corrected quantum computers go online, potentially allowing us to reconstruct the exact quantum fluctuation spectrum that birthed galaxies billions of years ago. Yet perhaps the most daring frontier lies in tabletop gravity experiments. By levitating microscopic spheres in ultra-high vacuums and cooling them near absolute zero, teams at ETH Zurich and Stanford hope to detect spacetime's predicted granularity. The idea, if quantum foam exists, it should impart random jitters to the sphere's positions, an effect so tiny it would manifest as displacement smaller than an atom's nucleus. Similar experiments using superconducting qubits are searching for vacuum fluctuations' gravitational backreaction, a phenomenon where virtual particles briefly warp spacetime enough to be measured. Success would mark the first direct evidence that gravity is fundamentally quantum. What unites these diverse approaches is their shared ambition to make the invisible tangible. From quantum simulators that recreate cosmic conditions in chips smaller than fingernails to telescopes that dissect ancient light for quantum fingerprints, each tool offers a unique lens on reality's turbulent foundations. The coming decade could deliver answers to century-old questions or reveal deeper layers of mystery. Either way, one truth is clear. The quantum fluctuations we once dismissed as mathematical oddities are now steering humanity toward discoveries that may redefine existence itself. From the seething quantum foam at the smallest scales to the birth of entire universes in a multiverse ocean, we've explored how quantum fluctuations force us to rethink everything we thought we knew about reality. These aren't just tiny disturbances in empty space, they're cosmic architects, shaping black holes, birthing galaxies, and possibly weaving the very fabric of time itself. What makes these theories so extraordinary isn't just their strangeness, but how they transform what we once considered flaws, randomness, uncertainty, unpredictability, into the fundamental features of existence. Some theories suggest these fluctuations are mere background noise, while others argue they're the universe's way of error correcting itself. Some see them as evidence we're living in a simulation, others as proof of consciousness shaping reality. And still others propose their threads stitching together hidden dimensions or wormholes between entangled particles. The wildest part, every one of these ideas, no matter how radical, is grounded in real math, each offering a different key to unlock mysteries like dark energy, the arrow of time, or the information paradox. What binds them all together is the humbling realization that the universe operates on levels far deeper and more bizarre than our everyday experience suggests. The same quantum jitters that make particles flicker in and out of existence could be responsible for the vast cosmic web of galaxies, or even stranger possibilities like bubbles of false vacuum decay rewriting physics itself. It's a reminder that reality at its core isn't static or settled. It's a dynamic, seething tapestry of potential where even nothingness brims with creative chaos. So which of these theories resonates with you? Do you find the holographic principle's cosmic pixelation more compelling, or the idea that entanglement might be threading the universe with microscopic wormholes? Maybe you're convinced that consciousness plays a role we haven't yet grasped, or that quantum fluctuations are nature's way of keeping reality stable. Whatever you're leaning, one thing's certain: the conversation is far from over. Every new experiment, every theoretical breakthrough peels back another layer of this quantum enigma, revealing even deeper questions beneath. If your mind is spinning from these possibilities, you're in good company. Even the greatest physicists grapple with these ideas daily. The universe doesn't owe us intuitive explanations. It's our job to keep questioning, testing, and wondering. So stay curious, because the next quantum revelation might be just around the corner. Want more deep dives into reality's strangest secrets? Hit subscribe, drop your favorite theory in the comments, and let's keep unraveling the cosmos together. Who knows, your question might spark the next big breakthrough.